Today we are going to discuss a supremum norm. So we are going to continue our study on norms on a linear space Kn. So we are going to define supremum norm. So sup norm. So we are about to we are going to continue our study on normed spaces. Normed spaces. Now we are going to define supremum norm. So or sup norm. The sup norm is the definition of sup norm. Sup norm. On Kn, we are going to define supremum norm on Kn. The sup norm is denoted by this one and read as sup norm. In Kn, you know K is ROC, Kn is defined as for x in Kn, sup norm of x is equal to maximum of modulus x of 1, you know x is x of 1, x of 2, etc., x of n. Therefore, it is equal to maximum x of 1, x of 2, etc., maximum modulus x of 1, x of 2, etc., modulus x of n. We are just taking this quantity as the maximum of the coordinates. So this is for all, this is the definition for sup norm for x in Kn. X in Kn. Now, we are going to show that this is a norm on. So norm on Kn. So we are going to prove that three conditions. One, positivity. So first of all, we prove supremum norm of x greater than or equal to 0 for all x in Kn. So we have this supremum norm of x is always greater than or equal to 0 since supremum, it is defined, supremum norm of x is defined as the maximum of modulus of x of 1, etc., x of n, x of n is defined like this. It's defined like this, and you know each components, each of the quantities x of 1, x of 2, etc., x of n is positive, so its maximum will always is positive. This is and since x of I, modulus of x of I is greater than or equal to 0 for each I is equal to 1, 2, etc., n. We have this one, supremum norm of x is greater than or equal to 0. And suppose that supremum norm of x is, suppose that sup norm of x, that is sup norm of x is equal to 0. So this implies, by definition, this implies maximum of modulus of x of 1, comma x of 2 comma etc. Modulus of x of n, this is equal to 0. And you know all these things are non-negative. X of 1 modulus of x of 1, modulus of x of 2, etc. modulus of x of n are non-negative, and maximum is equal to 0. So this will imply that each of the term modulus of x of 1, modulus of x of 2, etc. modulus of x of n equal to 0. So this implies modulus of x of I, this is equal to 0 for I is equal to 1, 2, etc. n, and that will imply that x of I equal to 0. So that will imply that x is equal to 0, because x is x of 1, x of 2, etc. x of n. Now the second condition you have to check is that of triangle inequality. So you consider norm of x plus y, subnorm of x plus y, and this is actually equal to maximum of modulus of x of 1 plus y of 1, comma etc. comma modulus of x of n plus y of n. So this is by the definition. So this, and you know, apply triangle inequality for the modulus on each of these terms. You can see that this is less than or equal to maximum of modulus of x of 1 plus modulus of y of 1, comma etc. modulus of x of n plus modulus of y of n, modulus of y of n, and this is less than or equal to maximum of modulus of x of 1 comma x of 2 etc. modulus of x of n plus maximum of modulus of y of 1 plus modulus of, comma modulus of y of 2 etc. modulus of y of 1. And this will imply that, so this is actually, the first quantity is actually supremum norm of x, and the second one is supremum norm of y, supremum norm of y. So what you're getting is supremum norm of x plus y, this is less than or equal to supremum norm of x plus supremum norm of y, supremum norm of x plus supremum norm of y. So we have proved the triangle inequality. Now we are going to prove that. So you let k belongs to k, k belongs to k, and x belongs to kn, x belongs to kn, and you consider supremum norm of kx, supremum norm of kx, and you know by the definition this is equal to maximum of modulus of k x of 1 etc. modulus of k x of n, k x of n. So this is equal to maximum of modulus of k into modulus of x of 1 etc. modulus of k into modulus of x of n. So this is equal to, you can take modulus of k outside, this will not alter the maximum because it is positive. So you have this maximum of modulus of x of 1 etc. modulus of x of n. So this is nothing but modulus of k into subnorm of x. So we have proved that supremum norm is a norm on, so this is a norm on Kn. So we have discussed various kinds of norms on Kn. So we have P norm for 1 less than or equal to P less than infinity, and you have supremum norm for supremum norm defined on, these are all norms defined on Kn. So you have a variety. So for any real number P, you have between 1 and infinity, you have norm P by the usual definition. So you have the definition in the previous class. So you have that is a norm on Kn, and you have supremum norm. Now supremum norm is also a norm on Kn. Now we are going to discuss by an example what is the meaning of these norms. Now, for example, you consider the unit circle on R2. So our space here is R2, or instead of taking K, N, you are taking R2, and you consider the set of all V such that norm V, P norm of V equal to 1. So you consider this set of all V, comma V in R2. V in R2. So you consider this set for P equal to 1, 2, 3, 4, etc. and infinity. So we are actually going to discuss P equal to 1, 2 and P equal to infinity, and using GeoGebra you can see what is 3, 4, 5, etc. Okay, so we are going to analyze what is, so this is actually the unit circle on R2 with respect to different norms, 1 norm, 2 norm, etc. So we are going to analyze what is actually unit circle is in this norm. So as the first case, you consider R2 with 1 norm. Consider R2 with 1 norm. And our set under consideration is set of all V in R2 such that norm V, 1 norm of V, is equal to 1. 1 norm of V is equal to 1. So since V belongs to R2, so it's a different ink. Since V belongs to R2, so you let V is equal to some xy, comma x belongs to -1, 1, y belongs to -1, 1. Now, what is the supranorm, 1 norm of V? 1 norm of V by definition it is x, modulus of x plus modulus of y. And from this, so if you take this as the set star, you are considering, so you may say that this is C, set C equal to. So if V is an element in C, so norm of V 1 norm of v, this is equal to 1, implies norm of x, modulus of x plus modulus of y equal to 1. So we have 4 situations. 4 situations. So we are considering norm v equal to 1 implies modulus of x, 1 norm of v equal to 1 implies modulus of x plus modulus of y equal to 1. So this x and y belongs to R2. So you have this varies in different norm, different quadrants. So suppose that this is the quadrant 1. Q1. Suppose that this is Q2. So we may use another color. So suppose that this is Q2, Q2, and suppose that this is Q3. Suppose that this is some Q4. Okay. First quadrant. So this is x-axis and this is the y-axis. So if xy is here, then so if v belongs to R2, if x comma y belongs to R2 is in Q1, first quadrant is in Q1, then you know that in the first quadrant norm of a modulus of x is x itself and modulus of y is y itself. So this implies modulus of x plus modulus of y, this is equal to 1, implies x plus y equal to 1. This implies y equal to 1 minus x. Y equal to 1 minus x. So if you take this as the point 1, 0. If you take this as the point 0, 1. And if you take this as the point minus 1, 0, minus 1, 0. And if you take this as the point 0, minus 1. 0 minus 1. Now you consider in Q2 what happens in Q2. So what is this equation? Y is equal to 1 minus x. Since x and y varies from minus 1 to 1. So you have this is your y is equal to 1 minus x. Y equal to, so this is the equation of y is equal to 1 minus x. So we can check all these things using GeoGebra. Now you consider in Q2. In Q2, in the second quadrant, so we have modulus of x is minus x and modulus of y is y itself. You know, therefore modulus of x plus modulus of y equal to 1. This is actually obtaining from norm v is equal to 1 norm of v is equal to 1. This implies minus x plus y equal to 1. So this implies x is y equal to 1 plus x. Y is equal to 1 plus x. And you know y equal to 1 plus x will be this one. This one is y is equal to 1 plus x. And in Q2, in Q3, In Q3 you have modulus of x is minus x and modulus of y is minus y. So therefore modulus of x plus modulus of y, this is equal to 1, implies minus x plus minus x plus minus y, this is equal to 1. So this implies in Q3 it is y is equal to minus x minus 1. Minus x minus 1. So that line will be, line segment will be like this. And in Q4, in Q4 fourth quadrant, you have norm of x is x itself and norm of y is minus y. Modulus of x is x, modulus of y is minus y. Therefore, modulus of x plus modulus of y equal to 1 implies you have modulus of x is x, modulus of y is minus y, so this is equal to 1, and that will imply y equal to x minus 1. X minus 1, and you are getting this one, this line segment. So so we'll draw it very neatly. Using GeoGebra we can illustrate all these things. And so in one norm, the set in one norm, the unit circle will be like this. Now you consider what is in two norm. That you know, it's very simple. In two norm, so we are going to consider two norm equal to 1. So our set under consideration is C is equal to set of all V in R2 such that norm V, two norm of V is equal to 1. And by the definition, two norm of V is modulus of x plus x the whole square plus modulus of y the whole square the whole raised to 1 by 2, since V is equal to xy. Vector V is equal to xy. And you know, therefore norm of V, two norm of V, this is equal to 1 implies modulus of x the whole square plus modulus of y the whole square the whole raised to 1 by 2, this is equal to 1. So this implies modulus of x the whole square plus modulus of y the whole square is 1. So from this you are getting, since modulus is positive, square is positive, you can say that this is x square plus y square is equal to 1, which is nothing but the unit circle. So you know, two norm defines the Euclidean norm. So two norm is actually the Euclidean norm. So in Euclidean space, the unit circle is, you know what is the unit circle? It is like this. Know that, no need of big explanations. That's why. So this will be like this. So we will draw it neatly later. So this is the unit circle in Euclidean space. Now you consider supremum norm. We will discuss the remaining norms using GeoGebra. So you consider the supremum norm. So what is happening in supremum norm? So you are considering R2 with supremum norm. R2 with supremum norm. So, and you are considering the set C is equal to set of all, C is equal to set of all V in R2 such that norm V, supremum norm of V, this is equal to 1. Is equal to 1. So this is under this set under consideration. So you let V is equal to xy. So what is the behavior of unit circle in supremum norm in R2 with the supremum norm? So you consider so norm of V is equal to supremum norm of V is equal to 1 implies maximum of modulus of x comma modulus of y, this is equal to 1. Maximum is 1. So this implies so there are two situations, either maximum is modulus of x or maximum is modulus of y. Suppose, so the case 1, suppose maximum of modulus of x comma modulus of y is modulus of x itself. So there is a situation. Therefore, subnorm of V, this is equal to 1, implies modulus of x equal to 1. This implies x will be equal to plus or minus 1. That is the first situation. Now, so in that case, that is modulus of x equal to 1. This implies x is equal to plus or minus 1. So in this case, our unit circle, this equation, so x varies between minus 1 and 1. So we have, suppose that this is x-axis, y-axis, this is minus 1, this is 1, of course it is minus 1, 0, this is 1, 0, and this is 0, 1, and this is 0, minus 1, 0, minus 1. So then between plus 1 and minus 1, between plus 1 and minus 1, x is equal to 1 is this line and this line segment, and you know this is x is equal to minus 1, this much part. Now starts from here, go up to here. Okay. Now consider the situation when maximum, second case is maximum of x comma, suppose case 2, maximum of x comma y, this is equal to some y, modulus of y, and this is your subnorm of V, subnorm of V. So this implies, therefore subnorm of V equal to 1. This will imply that modulus of y, this is equal to 1. So that implies y equal to plus or minus 1. So when y equal to 1, you are getting this segment, and when y is equal to minus 1, you are getting this segment. So this is the unit circle in R2 with subnorm. So this is, so that is the behavior of our C in so this is our C in R2 with supremum norm. Okay. We have other norms. Now we are going to check what is 3 norm, what is the shape of 3 norm, what is the shape of the circle, unit circle in R2 with 3 norm? What is the shape of unit circle in R2 with 4 norm, etc. That you can use GeoGebra. And in GeoGebra, one advantage is you can directly plot modulus of x. So you can plot these curves. You are going to plot these curves. First one, modulus of x plus modulus of y, this is equal to 1. We are going to plot this one. The second case, you are going to plot a modulus of x square plus modulus of y square, the whole raised to 1 by 2. This is equal to 1. And this, in order to plot this, it is enough to plot x square plus y square equal to 1. And in GeoGebra there is a facility which can plot x cube. So what is the norm? 3 norm of v. This is equal to modulus of x cube plus modulus of y cube, the whole raised to 1 by 3. Whole raised to 1 by 3, and you can plot this also. 4 norm of v. This is actually equal to modulus of x whole raised to 4 plus modulus of y, the whole raised to 4, the whole raised to 1 by 4. So we are going to plot, and we are going to we will plot x is equal to in infinite subnorm. We will plot x is equal to plus or minus 1, x is equal to y equal to plus or minus 1, where x belongs to minus 1 1, y belongs to minus 1 1. So we are going to do all these things in GeoGebra, and we can see what happens. So this is the GeoGebra window. So here you can input either you can first we plot what is norm modulus of x plus modulus of y equal to 1. So you consider modulus of x plus, so it is better to zoom. Zoom here. So put modulus of x plus modulus of y, that is equal to 1. Equal to 1. So you can see that in the algebra section you can see absolute value of x plus absolute value of y is equal to 1. So this is your unit circle in R2 with 1 norm. Now you consider the unit circle in Euclidean space that you know, x square plus y square, this is equal to 1. So you know this is the unit circle in R2 with the usual Euclidean norm. So this is the first one. This box is the unit circle in R2 with 1 norm, and this is the unit circle in R2 with the 2 norm, that is in Euclidean space. And you consider subnorm. Subnorm is x equal to 1, you draw x equal to 1, and you draw x equal to minus 1, and you draw y equal to 1, and you draw y equal to minus 1. Okay, so since x and y varies between +1 and -1, our region under consideration or our curve under consideration is this one. So we can mark that too. So this A, B, this C, this D, and E. So this A, B, C, D, A. You have a rectangle, a unit square. So have this. We have this. So this is the unit circle in R2 with SUT norm. So this one ABCD. Now you just plot, consider R2 with 3 norm. So there the curve will be modulus of x raised to 3 plus modulus of y raised to 3 the whole raised to. So we keep a bracket, raised to 3 the whole raised to 1 by 3. So consider this 1 by 3 and is equal to 1. This here we can plot this one more. Modulus of, so you start with the bracket, modulus of x raised to 3 plus modulus of y raised to 3 all raised to 1 by 3. 1 by 3 and that is equal to 1. So that you forget. So this is the unit circle in R2 with 3 norm. This one. And consider what is in 4 norm. What is the 4 norm in R2 and what is the unit circle with respect to 4 norm in R2. So you consider this. So you can plot modulus of x raised to 4 plus modulus of y raised to 4 all raised to all raised to 1 by 4 1 by 4 that is equal to 1. So you can see that this one is the SUT norm, unit circle with respect to the norm 4 norm on R2. You can see what is happening here, and you may check one more just for fun. You may check one more. Modulus of y, modulus of x raised to 5 plus, in the meanwhile you can see that what are that curves, modulus of x raised to 5 plus modulus of y raised to 5, so whole raised to 1 by 5, we will take raised to 1 by 5. That is equal to 1. So you can see this one. So this is the unit circle with respect to 1 norm. This is unit circle with respect to 2 norm. Unit circle with respect to 3 norm. Unit circle with respect to 4 norm. Unit circle with respect to 5 norm, etc. This is the unit circle. This one. We are thinking about the border. Unit circle with respect to SUT norm on R2. So that's a nice experience. Okay. Now let us stop here for the time being. So have a nice day for all of you.